Hello students. So I have an interesting surprise for you today. I've been thinking about this. I'm sure you're missing IIT Bombay quite a lot. And for the people who are watching these videos on satellite transmission, you might be wondering how IIT Bombay students, where do they work and things like that. So this is our really popular well lab, Wadhwani Electronics Laboratory. And you can see these whole bunch of setups here where all the students do their experiments. So I thought it will be great or rather interesting video to show you the lab so you don't feel IITB sick. Today we are going to talk about, start talking about devices, semiconductors and devices using semiconductors. So the first device we're going to talk about is PN junction. So here is I have a PN junction diode that I would like to show you, and if you observe this diode carefully when you're back, or if you have a chance to look up one device, you will see a ring around the device, okay, on one side. And generally whenever you see that ring, so for example in this particular device the ring is on the left side, and that is a cathode of the diode. Okay, we have anode and cathode. Anode is the positive terminal, cathode is the negative terminal, and the ring indicates a cathode. Here is another diode that I would like to show you. Now it's a little bit tiny device. Again, in this case also you will see a black ring on one side, and this one is a Zener diode. Okay, so I'm going to explain all these devices to you in this lecture. Generally, there is a companion course going on in every university, which is a deep devices course, where you learn how the devices are manufactured, how is the electrons, holes transport going on in a semiconductor, and things like that. And there you learn a lot of equations. In this particular class, I could just start from equations of diodes or bipolar junction transistors, but then I feel that you will probably miss out a lot if I don't give you some intuition. So what we're going to do in this class is we're going to go through intuitive level understanding of these devices, how the transport is happening, electrons, hole transport, majority carrier, minority carrier transport, that's happening. And by that you will be able to recall or remember how these devices work, and then we can get into a circuit level model of the devices, and then we start using those devices in different circuits. Thank you. In today's lecture, I'm going to talk about semiconductors, P-type semiconductor, N-type semiconductors, and then how do we make diodes. Just a few minutes ago I showed you a diode in the lab, and I was trying to describe it to you, and here is a diode that you can buy as a component, and it kind of looks like a cylinder, and then there is this terminal that's coming out of it. Okay, and in this particular case, the one when I showed you, it had a white or a silver ring around on one side, and the thing I was trying to tell you was this ring generally denotes a cathode, K, or cathode. Terminal, if that is the cathode, then this is the anode. The symbol for the diode is like this. And as I have explained to you, you look from this way, you see a K, and that's your cathode. Cathode denotes negative terminal. And if you look from this, you see an inverted A, that's anode, and that's a positive terminal. And this arrow is showing the direction of the current that it can carry. Now, before we get into the diode, let's talk about silicon as a semiconductor. Now, if you look at silicon as an element, it has 4 valence electrons. Okay, so they are in the outermost shell of the atom, and if you add 4 more valence electrons, then it's very happy. You know, all the bonds are complete. So for example, if you have one atom and then somehow it connects with 4 other atoms and shares the electrons with each other, okay, like this. Now you have this is each atom, silicon atom, okay, like this, silicon silicon, each atom, and it connects with it shares its electrons with the neighboring atoms like this, and of course this will continue going on like this, okay. Now these 4 valence electrons are shared with the neighboring atom, as a result of which you form these covalent bonds with the neighboring silicon atom. Now things are all fine like this, and if you just take a silicon, pure silicon as is, then it, at really cold temperature, it probably feels like an insulator. There is no current flowing through the silicon. Let's say you take a blob of silicon, then there would not be any current flowing through it. However, at room temperature, some of these covalent bonds can be broken at room temperature just because of the thermal excitation of the electrons, and they are moving around with the thermal energy, and sometimes they escape the bond, and whenever they escape the bond, the electron becomes free, and wherever there is a absence of electron, we call that as a hole. And holes are positively charged, electrons are obviously negatively charged. As a result of these free electron hole pairs, we have some current that can flow through this silicon at room temperature, and that's why we call it semiconductor. Okay. In a perfect conductor, you will have tons of electrons, and then the current will be carried using those electrons as a transport medium. That's why they are metals, because they have a lot of free electrons. In a semiconductor, at room temperature, some of these covalent bonds can be broken because of the thermal excitation, and then there could be some amount of current that would flow in a semiconductor. Okay, so for example, in this particular case, we are talking about silicon as a semiconductor. So as it is, it's not a very useful we cannot really use it anywhere just as a semiconductor. The cool thing that happens is when you introduce some impurities in this silicon. So there is one equation that is useful here, which is for silicon as a semiconductor, is P times N is equal to Ni square. And this Ni is called intrinsic carrier concentration, and the value of Ni is equal to 1.5 10 to the power 10 per cm cube. So in every cubic centimeter there will be 1.5 into 10 to the power 10 carriers, intrinsic carriers at room temperature. Okay, and P and N happens to be, P will be the hole concentration and N will be the electrons concentration. All right. So by itself, silicon is not, as a semiconductor, is not very interesting. Okay, because it has only few carriers which can carry current, and that's why we call it a semiconductor. Now let's say we adulterate this silicon. Okay, I use the word adulterate because we are going to make it impure, intentionally impure. And the element we are going to use is boron. So boron has only 3 electrons in its outer shell. You will have one missing electron in the silicon when you introduce a boron, and boron is called an acceptor impurity. I'm kind of visualizing it for you. You take silicon and you put some boron into it, and the concentration of boron in this silicon is given by Na. Na is equal to some number per cm cube. All right. So in that case, since it's an acceptor impurity, the concentration Na is pretty much equal to the holes, which would be the holes in the semiconductor. Okay, so we call them, holes are denoted by P, and since we are adding boron, it's a p-type material. Also, as I said, this is a p-type material. Okay, p-type semiconductor. Okay, so this P denotes p-type and this P denotes the hole concentration. So in this particular case, you will also have electrons, and electrons will have N sub P. Okay, so these are electrons. Again, these electrons are happening because of thermal excitation, you know. So since we are dominating the silicon piece using acceptor impurities, we can call this as a majority carrier, and this would be your minority carrier. Okay. Similarly, we can talk about donor impurity, where donor impurity, and that would be N-type semiconductor that we will form. In the donor case, we would add phosphorus. Okay, phosphorus has 5 electrons in its outer shell, so we have 1 extra electron. Now, when you dope silicon with phosphorus, okay, then you will have this is called Nd. That's a donor impurity, and that is again given as number in cubic centimeter. Okay. So in this particular case, we would call it N's of N. This would be your Nd, and P of N would be the holes due to thermal recombination in the N-type semiconductor, and they would be, this would be the holes, and they would be the minority carrier. Okay, and Nd would be, the donor elements would be the majority carriers. So why am I telling you all this stuff? So interesting part is, if you look at a p-type semiconductor, okay, the p-type semiconductor will have minority and majority carriers. The majority carrier would be P sub P, along with minority carrier would be N sub P, and multiplication of this is again equal to Ni square, which is the intrinsic carrier concentration. Okay, so in this case we can say that if P sub P is your acceptor impurity, we say this is Na times N's of P is equal to Ni square. So minority carriers in p-type semiconductor, which are electrons, they are equal to Ni square divided by N's of A, which is the concentration, the doping concentration of p-type material. In this case, it's boron. All right. Similarly, we can prove that for N-type semiconductor, we have N's of N times P's of N is equal to Ni square. This one is still the same, intrinsic concentration, which depends on the temperature, and the minority holes carrier concentration is given by Ni square divided by, what is N's of N? That is your phosphorus doping, which we call it donor. Nd. Okay. So now that we got all this together, let's look at what happens when we put a p-type and n-type semiconductor together. And I'm going to show you a grossly exaggerated image, however, to make a visual impact on you. Okay, and then we have this piece of metal connected on one side, and this is piece of metal connected on this side. Okay, and these are our two connections to the element. So this is a p-type semiconductor, and this is n-type semiconductor, silicon. Okay, as I said again, this has acceptor impurities and this has donor impurities. So acceptor is boron and this is phosphorus. There are two types of actions which are happening in the semiconductors. The first one I would like to explain it to you is called, let's take an example. Let's say you bought perfume and you opened the perfume bottle and you just sprayed it. What exactly happens when you spray the perfume? So think about it this way: the concentration of the perfume just outside the opening of the bottle, okay, is the highest. Okay, and as soon as you spray it, the perfume molecules, they will diffuse. The key word I'm trying to tell you is the diffusion. Okay. Another example would be, let's say you have a glass of water and you drop some ink in a glass of water. So wherever that ink drop is entering the glass of water, the concentration is really high, and rest of the water does not have anything, any ink molecules, okay, or pigmentations. And in a short amount of time, those ink molecules will diffuse in the water, and eventually it will all, the ink will all completely dissolve in the water, and you will see a consistent color. Okay, so this mechanism is called diffusion. And the diffusion happens when you have high concentration on one side and then you're going to low concentration. This is when the diffusion happens. So in terms of our semiconductors, the majority carriers, for example, in this particular case, you have holes here in the p-type and electrons in the n-type. They are majority carriers. So they will diffuse across this junction to the other side. And then what happens? Let's draw the picture with different colors so it will be clearer for you. So I'm just going to magnify the interface for you right here. And let's say this is our interface, and I'll put some dots here. So this is the p-type and this is the n-type. Okay, let's use yellow for the p-type will have holes originally, is dominated by holes. I'm just showing them with yellow to begin with, and n-type will have lots of electrons, and let's use a different color here. We will just show them like this. So there is a high concentration of electrons. So as soon as you bring these together, what we expect to happen is diffusion, and because of diffusion, what we will see then is some of these holes, okay, they will cross the barrier, and some of the electrons will cross the barrier like this. Okay,
the holes will go to the N type because the concentration of holes is very high on the P type, and the concentration of holes in N type, which are the minority carriers, is very low. Okay, so we expect something interesting like this will happen. And this particular area around the junction, okay, will not have any carriers. So holes have left. Some of the holes at the junction interface have left to the N type, and probably they got recombined or with electrons and things like that. And similarly, when electrons came back to the P type, they kind of sat into some of the holes location. Okay, so what we see then is you will see negative charges on this side because the electrons have arrived here, and on the other side, on the N type, since we have lost a few electrons, you will see positive charges. Okay, you'll see positive charge here. Okay, let's put circles around the charges so that we don't get confused. So this is positively charged, and the left side, which is P type, will be negatively charged. And just so that nobody gets confused, these are holes, and the magenta, these are electrons. This area, this colored area here, is called depletion region. And since we have this charge buildup here, you will see some kind of, let me rewrite this here. So you have depletion region, which means all the mobile charges are depleted from the interface section, and as a result of depletion region, we have built-in potential because of separation of charges at the junction, and we call that V0. And as soon as there is a potential difference, there will be some kind of electric field over here. Okay. Now, we only talked about so far one method of transport here. Let me erase this. So what was the method of transport over here? We get I diffusion. Since the charges move from one side to another side, we get current, and the mechanism of movement of charges is diffusion. So we call it I diffusion. Now this I diffusion, as I already said, will set up the space charge region or built-in potential with the polarity as shown, and this would give you electric field in this direction, because positive on the right side and negative is on the left side. Okay. As soon as you have electric field, what happens? I don't know if you have ever done it when you were kids. Every time there is rain, a lot of rain, there is water flowing. Let's say you make a paper boat and then you drop the paper boat in flowing water. The paper boat will just get carried away, right? It will carry and it will go through. It will follow the current. In this particular case, our electric field is like that current. Okay, and the paper boat here would be our minority carriers. So minority carriers. And where do these minority carriers come from? As I said again, these minority carriers are thermally generated. Okay, so these thermally generated minority carriers, which are already there in either P type or N type, they will start getting affected by the by the electric field, and they'll start flowing in the opposite direction. This particular method of conduction is called drift. Okay, so we will see something called drift current here. I drift. And as the name suggests, just like our paper boat will drift in a strong current of water, in this particular case, the minority carriers will drift in the existing electric field, which have happened because of these other things. So at equilibrium, we say that I diffusion is equal to I drift. Let's apply some external potential and then see what happens. All right. So the first case we are going to talk about is another second case. The first one was open circuit. So in this case, we would take a semiconductor and then we would apply this is P and this is N. So I'm going to apply a battery potential here, and I'm going to apply negative potential here and positive potential here. So this is negative terminal of the battery, this is the positive terminal of the battery. Let's call this VR. So since we are applying negative potential to positive node of the or p-type material, we call this a reverse bias. So PN junction under reverse bias. Let's see what happens in this case. So in this case, originally we had this depletion region over here. Let's use a different color. This was our depletion region. Okay. Now by applying opposing potential, we would increase the depletion layer. The depletion region here will increase, and the depletion here on the N side also will increase. Okay, and we will have since we have connected positive to the N type, you will have more positive potential on this side. Okay, and similarly we have more negative potential here, something like this. Okay, so this reverse bias voltage will add on to the built-in potential at the interface, and we would see the barrier. Originally the barrier was V0. On top of that, we have added reverse bias potential. So by putting the PN junction in reverse bias, we have increased the built-in potential. We have added on top of the built-in potential V0 plus VR, and what this would do is your I diffusion current will reduce substantially, almost to zero. Okay, because we don't have any excess carriers or the concentration of holes on the p-type and electrons in the n-type, because they all will get sucked into the battery. Okay, because we are applying negative potential to the p-type and positive potential to the n-type. So as a result of which the diffusion current will drop down to zero. However, this thermally generated minority carriers, they're still there in that region and they will continue to flow. So what we expect to happen is the following. We will have very small diffusion current, and our original drift current will continue to flow in this direction. Okay. As I said again, the I drift is minority carriers and they are they are moving around under E field, electric field. If you look at this carefully, the only current you can say which is flowing in this direction will be I drift. Okay, so we can write I reverse bias is equal to I drift. Now this is still not that interesting because there is no current flowing, and the current which is flowing in the reverse bias case is again really small. Okay, so now we will go to the most interesting use of the diode, which would be PN junction under forward bias. In this particular case, something very interesting happens. So we take the PN junction, and here we are going to connect. This is P type and this is N type. So in this case, we are going to connect P type to positive and N type to negative. Positive and negative. Okay. So by connecting positive terminal, we are flooding the P type with positive charges, and by connecting the negative terminal, we are flooding the N type with negative charges. You can imagine a battery as positive charges and negative charges separated, and that gives you the potential difference. Okay. All right. So what will happen then? Now I'm flooding the positive charges in the P type, and I have flooded the electrons in the N type. Obviously, we are making P type have lot more holes, and N type we are going to make, we're going to add more electrons. So you can immediately think that, hey, my diffusion should increase. The diffusion current should increase, right? So you will see there will be a large diffusion current. I'm going to show it here on the top. That should flow I diffusion from P to N. The holes will flow from P to N type, and then they'll get replenished again, flow this way. And as a result of which, you will see a current flow across the junction. The width of the depletion region will reduce substantially. Okay, so you will see really small region here which will have depletion region. So this would be your minus charges here, and here will be the plus. Okay. So the drift business still continues going on. So you will see the same amount of drift as before. And that's happening because of the thermally generated carriers, minority carriers. Okay. So the I drift will probably be the same going from in the opposite direction. Okay. And as I said again, we introduce this forward bias voltage. Let's call it VF. VF is our forward bias voltage, and our barrier voltage will now change. The barrier voltage is here at the interface. That would change from V0 to V0 minus VF. Okay. And we will also see reduced depletion region width. All right. So this becomes very interesting now when you put all of it together. What's the interesting part? If you forward bias the diode, you will have current flowing from P to N, from positive terminal to the negative terminal. But if I reverse bias the diode, there will not be any current flowing. Okay, so the flow of current is unidirectional. It's only in one direction. It will not flow in both the directions. Okay, and we can model this part, this both diffusion and drift, with a very simple equation. Okay, I is equal to Is. I'm going to explain you all the terms. V divided by Vt minus Is. Okay. And this part is called diffusion current, and this is our drift current. Okay, and the model is, I'm applying voltage V across the diode like this, and the current is flowing in this direction, I, and this is the model that we are talking about. I is equal to Is exponential V divided by Vt minus Is. V being the potential, V forward bias potential that we have applied in this case. Okay, so let's see how does this equation really fit into all the things that we have learned so far about the diode. Okay, before that, let me explain. Vt is called thermal voltage. And it's given by Kt over Q. K being the Boltzmann constant, T being the temperature in degrees Kelvin, and Q is the charge, Coulomb. For temperature, T is equal to, let's say, room temperature. We generally call it 300 degrees K. Vt is given by 26 millivolts. And we use this number quite a lot. So just keep that in mind. So you don't have to write Boltzmann constant, T, Q, all those numbers. If you know value of Vt at room temperature 300 K, then you can just use the proportionality and then figure out value at any different temperature. Let's go back to our equation here, the diode equation, and see if it's really doing what we think. Is it really modeling the whole phenomenon, the reverse bias and forward bias? Okay, so let's I is equal to Is exponential V divided by Vt minus 1. Okay, if V is negative, which means we are in reverse bias condition. Okay, so e to the power V divided by Vt will be much less than 1 because V is negative, and in that case your current I will be equal to minus Is, and that would be your saturation current, also called as SAT current, saturation current. So this makes sense. And under forward bias condition, your exponential V divided by Vt, if V is larger than Vt, then this is very large compared to 1. So we can simplify. The diode current is equal to Is exponential V divided by Vt. So this would be your under forward bias condition. Okay. So the key part here is, as voltage keeps increasing, the current I will exponentially increase. Okay. Let's take a numerical example and then things will become very clear. Given that Is is equal to 2 10 to the power minus 16 amperes. As I said, Vt is equal to 26 millivolts at room temperature. And I'm going to numerically write down what would be the value for V and I. When V is equal to 26 millivolts, the current value will be 5.5 4 10 to the power minus 16 ampere. It's so small, so tiny. If we change this value to, let's say, 500 millivolts, okay, then still the current value is small. This will become 45 nanoamps. Nanoamps, 10 to the power minus 9. Now, if I just went from 500 to 700 millivolts, then this current increases to 98 microamps. From 700 to 750 millivolts, this increases exponentially now, 675 microamps. 750 to 800 millivolts, wow, this becomes 4600 microamps. And now from 800 millivolts to 850 millivolts, this becomes 32 milliamps, very large. Okay, so we call this process that our diode is turning on, turns on. And you can see around this value here, 700 to 750 millivolts, the diode really turns on. I want to give you a physical example of this diode. If you look at any buildings, right? For example, if you stay in a skyscraper, then generally what happens is on top of the building there is a tank, water tank, and generally there is a pipe that's pumping water, okay, into this water tank, and then that water tank is what is used to supply water to all of you. Okay. Now, if you think about this, if you keep pushing water from here, and whenever the water pressure drops, all the water will drain out, right? So they use something called NRV, no return valve. Okay. So this NRV looks like a very simple device, and I'm just going to draw it for you, and then it will be clear to you how this looks like a diode. Okay, so it has an edge like this, and there is a circular flap that it has, something like this, and the water flows from this direction and goes out this direction in this pipe. Okay, so this particular flap is held in place using a spring, which means if you are pushing water up, then it takes some effort for this flap to open up like this. Okay, but once you apply enough force of water from the bottom, the flap will open and the water will start flowing up. However, as soon as the water pressure at the bottom drops, the flap will come down and it will seal like this. Okay, so you will have this, and this is your ring, and then the flap will seal the place. So there is no water that can return back down. So our diode is kind of doing the same thing. When you apply a positive potential, it turns on after a while. Initially there is some resistance, and as soon as it reaches some critical voltage, the current starts flowing, the diode is in full operation. When you apply reverse bias, for example, for this NRV, if the water is going from the top to bottom, then it won't allow the water to flow out on the other side. Okay, so just wanted to give you a physical example, which is more of a mechanical or fluid dynamics type of example, which all of us are already using in our day-to-day life. Okay, so if we plot this current on like this, okay, so again I'm doing this, I'm applying positive minus, and then I'm applying it to a diode like this. This is V and this is current I. So we are plotting I on the y-axis and V on the x-axis. Why are we plotting I on the y-axis? Because V is what we are applying and I is the current that flows as a result of it. So when V is sufficiently small, sufficiently below certain value, for example, in this case, let's say we said, maybe somewhere 700 millivolts, let's say. Okay, in this particular case, the current is quite small, and we kind of draw it this way. Let me use a different color. And even whenever the V is negative, we see reverse bias current flowing. Okay, and as soon as we approach this close to 700 millivolts, then we have this exponential effect with the current flowing, and then you will see something that looks like this. Okay, and this would be our forward bias condition, and this would be the reverse bias. Here the assumption is that I can apply a reverse bias to the diode as much as I can on the left side. So for example, I will not make notations here, just to show you. Okay, so what I'm showing is something like this, and originally I showed you that, hey, the current is really small, close to zero, like this, and this is our voltage V, and this is our current I. So in this case, we are assuming that I can apply negative voltage or reverse bias potential for the diode as much as I can, but in reality that is not possible. So for example, if I'm applying a positive and negative potential over here, okay, which is the high reverse bias, what will happen is you will have very high electric field in the diode, right? If you apply really large reverse bias voltage, then you will have really large electric field. And what happens as a result of high electric field? As a result of high electric field, you will have the structure inside this semiconductor will start breaking. The bonds will start breaking, okay, due to the high electric field. Now, as soon as the bonds break, we have more carriers which are part of this electric field, and they will start flowing under the influence of this electric field. They will have really high speed because velocity is given by mu e, okay, for the charge carrier. So if electric field is really high, mu is the mobility, the velocity of the electrons will increase substantially, and under this condition they will start bumping into the atoms, and they will start breaking more bonds, and then there will be more carriers. So all this action happens like an avalanche. If you have seen Avalanche on Discovery or Nature TV, it's a small, like a ball of snow, which will start coming down, and along with it, it will carry a whole bunch of more snow, and then eventually the avalanche starts. So similarly, in this particular case, we will see an avalanche effect, and I'm going to show the avalanche effect with a different color. What you will see is something like this happening, okay, and this would be your avalanche effect. Under extreme reverse bias. Okay, so this voltage at which this breakdown happens, this is called V breakdown, is really decided by the doping concentration in our P and N junction. So this voltage V breakdown is high when you have moderate doping concentration for P and N. Now we can take advantage of this effect, and if you remember at the beginning of the class, I showed you something called Zener Diode. So if I increase the doping concentration, which is Na and Nd for my diode, okay, then this voltage breakdown, which could be 20 volts, I can bring it down substantially, and you would get something that looks like this, okay, and this would be your Vz So the avalanche is happening when there are moderate doping levels in the p-n junction, and we can intentionally increase the doping level in the diode to high doping level, and then we can reduce this breakdown voltage to V Zener to lower voltage. Okay, so this V Zener generally is 3 to 8 volts type of range, and we can actually use this device to get a reference voltage between 3 to 8 volts, because this is something that will happen over and over again. Every time you put it to reverse bias, the current will flow. Now, key part you have to remember in both these effects is you have to limit the amount of current flowing through the diode. What I mean by that is, if you just take a diode like this, and if you apply a reverse bias potential like this, VR, okay, now this is a ideal voltage source. As soon as I take this reverse bias potential beyond certain value, there will be huge amount of current flowing in this diode in this direction. Okay, now that huge amount of uncontrollable current can burn the device out, because it's going to flow through really small area and it will burn the device out. Okay, and then the device is of no use. So what you generally do is you put in a resistor in the path somewhere. So you can put a resistor R. For example, if you're going to use this as a Zener diode, then you would like to put a resistor. What the resistor will do is it will limit the amount of current flowing through the diode. And the amount of current that will be flowing through the diode will be, you subtract the Zener. So for example, VR minus VZ divided by R. That would be the current that would flow through the diode. Another interesting thing we should talk about in the diode model is the following. Like this, and we are applying, I'm going to denote the values ID, and this is our cathode, and this is our anode. Okay, and we are applying potential VD like this. So as I said earlier, the drain current, the diode current is given by IS exponential V diode divided by VT minus 1. As I have already mentioned, VT is equal to KT over Q, 26 millivolts at 300 degree K. Now what is this IS saturation current business? I'm going to explain you that. Okay. So let me explain it to you intuitively rather than writing a whole bunch of equations which you can review on your own looking at any device book. So this current IS is given by, IS will increase if the area, the cross-section area of the diode is increased. So of course there is an A. IS has Q term in it. It has also Ni square, and then Dn divided by Na Ln plus Dp divided by Nd Lp. Okay, let me explain what this means. So A is area of the diode. Okay, and what is Ni? Ni is the intrinsic carrier concentration. Then when we talk about Na is acceptor doping concentration. Where does acceptor come into play? In the p-type part of the diode. Okay, and Nd would be your donor. And this would happen in the N-type. Okay. Now, what is Dn and Ln? Okay. So Dn and Ln are related to the diffusion aspect of the transport. So for example, Dn is called diffusion constant and Ln is the diffusion length. And the way to understand that, and similarly you have dp and lp. For example, if you have really high n-type carriers on one side, and so across the junction it's going to start dropping like this and it will approach the final value here. Okay. So the diffusion constant describes this particular characteristic. Would it be this way? Would it be this way? That is described by Dn and Ln. Okay. And what is the diffusion length? So Dn and Ln would be for the n-type. Similarly, you will have dp and lp for the p-type. Okay. So this is the way you can figure out what your saturation current Is of the diode is. Thank you.